further ado, I'd like to introduce our second lecture stream leader, Cameron Gordon, who is here from Austin, Texas, but is also the program's distinguished Rothschild professor.
Thank you.
Telling us about the three manifolds.
Okay, well, thank you. I'd like to thank the organizers, Liam and the organizers, for inviting me to take part in this winter school. It's going to be great fun. It is winter, so I'm gonna just. Well, it's nice. I guess I should say it's nice to be back. I was here many years ago in Cambridge. I knew Newton rather well, actually, and so yeah, it's nice. Anyway, it's nice to be back. So what I want to do today is just give make some very general remarks about three manifolds. Make some remarks about left orderability. And in general, I want to sort of get to. I mean, in fact, I mean these lectures in the stream that we're giving here, I think, is going to be perhaps geared towards at least understanding the statement of this conjecture. So M prime three manifold. So whatever that means. Adam, this means not an L space. This means co-orientable foliation. Rachel's going to talk a lot about foliations. This means that the fundamental group is left orderable. I'm going to say something about that today. But let me just first give some very general background on three manifolds and connected sums and so on. This is going to be not particularly deep. But so the first thing, let's remind you that in dimensions less than or equal to 3, all three sort of categories are equivalent. The smooth category, the PL category, the sort of locally flat topological category are all the same, so we don't have to say which category we're working in. You can choose. Throughout, I'll always use M will be a M will be a closed, connected, orientable, a three manifold. Unless otherwise stated, sometimes I'll say not necessarily closed, but if I don't say that, it'll be closed. And this is a generational thing, of course. You know, three manifolds nowadays are called Y. But in my day, they were called M, as Raymond will attest. So they're going to be M. So let me just remind you about connected sums and prime decompositions. So if we've got two manifolds, M1, M2, again, they're going to be connected and orientable. Actually, so not necessarily closed. Not necessarily closed. And I guess in this case, they better be oriented. Then let me remind you that you can form the connected sum of these two manifolds by you choose three balls in M1 and M2. So you let BI and MI be a three ball, and then you remove the interior, your interiors of these. So the connected sum of these two manifolds is, by definition, M1 minus B1 closure union M2 minus B2 closure, where H is a homeomorphism from the boundary of B1, the two-sphere that's the boundary of B1, to the two-sphere that's the boundary of B2. It's an orientation reversing homeomorphism. Okay, and This is a very basic construction. In dimension 3, you don't have to say any more than that. It's well defined. In higher dimensions, you have to be a bit more careful. But so this turns out to be, this is well defined in the oriented category. It's associative. It's commutative. It has a unit, namely the 3-sphere. And this gives rise to the obvious notion of prime. So that's the first word up there, prime. So you say that M is prime if it cannot be decomposed non-trivially as a connected sum. So M is prime if M homomorphic to M1 connected sum M2 implies that M1 or M2 is just the 3-sphere. Okay, that's and one of the most basic theorems in three-dimensional topology is Alexander's theorem that S3 is in fact prime. So S3. Again, famously, of course, as frequently happens in mathematics, I mean, he first claimed a false theorem. He first claimed that any 2-sphere in S3 was isotopic to the standard 2-sphere. And then he realized that, well, he was wrong, and he constructed a counterexample, the Alexander Horn sphere. So, so don't worry if you claim a false theorem, as long as you find the counterexample yourself. That's all right. But in the smooth category, in the locally flat topological category, it's true. So anyway, there we go. Now there's again a theorem. It's always attributed to Kneser and Milner, prime decomposition. So M. Now here M. Remember, M is going to be closed now. If I don't say it's closed, it's closed. There, it wasn't necessarily closed. Oh, by the way, and I'm going to leave. In this lecture, many statements. I'm going to just make many statements, and the proofs are going to be in the exercises. So there we are. I'll hand these out later. By the way, and some of them are going to be easy, and some of them are going to be hard. So don't worry if you can't do them. So M again. I suppose here M should be oriented though. Okay, then the theorem says that M is actually a connected sum of prime manifolds. So these guys Mi are prime and not S3. And if you do that, then these M's are unique. The MIs are unique, so the MIs are unique. Well, up to, of course, you can reorder them because connected sum is commutative, so up to order and orientation preserving homeomorphism. And of course, S3 is the case n equals 0, just the empty connected sum. So that's the Kneser-Milner theorem. Beautiful proof by Kneser. He stated the uniqueness, but he didn't prove it. And then Milner actually gave a proof. One of the themes of this, I mean, I mentioned that this statement is a statement about the fundamental group. The fundamental group is left orderable. And so let's just, as we discuss three manifolds here in this elementary kind of way, let's keep on mentioning the fundamental group. Well, let's just notice that the fundamental group of a connected sum in dimension 3, it's just a free product, right? If you remove a 3-ball, you're not going to change the fundamental group. And then when you glue together along a 2-sphere, the 2-sphere is simply connected. So by Van Kampen, you just get the free product of the factors. Okay, there's a nice sort of, well, I don't know, not quite converse to this, but okay. So this says that if okay, and so let me just state it. So there's a theorem. So this is the Knaser conjecture. It was proved by Stallings, which says that if, again, M is a closed three-manifold, so if pi 1 of M splits as a free product, then in fact there's a corresponding decomposition as a vectored sum. Then M is something with M1, vectored sum M2. So you get this very nice Knaser got a little bit of a bad rap here, actually. He wrote, Knaser wrote one paper in three-dimensional topology, and it's just a beautiful paper. But unfortunately, for him, he used Dane's lemma in part of it. And of course, while he was writing the paper, in fact, he was correcting the galley proofs of his paper. And I guess he began thinking about Dane's lemma again, and he realized that Dane's proof was false, was fallacious. And so he quit three-manifold topology, which was drastic, but that's what he did. And but meanwhile, somehow his paper got the reputation for being wrong, and in particular, he actually proved this. Although it became known as the Knaser conjecture, he actually proved this modulo Dane's lemma, sort of. And of course, it was eventually proved by Stallings using Dane's lemma. So he gets a slightly bad rap on that. Let me jump way ahead here, and we live in the post-Perelman era, so we're allowed to use all these great theorems. Let me just mention here that if you've got a closed three-manifold, if pi 1 of M is finite, then the universal cover M tilde is actually homomorphic to S3, and the action of pi 1 of M on the covering action on S3, pi 1 of M acts on S3 as a subgroup, sort of linearly, as a subgroup of SO4. So the three manifolds that arise in this way were classified a long time ago. They're sort of familiar manifolds. I'll mention lens spaces are the obvious examples. I'll mention those in a moment. But this is a particular case of the geometrization theorem that Perelman proved. And in particular, then, this is the Poincare conjecture that pi 1 of M is trivial if and only if M is the three-sphere. That's the trivial part. And so psychologically, it's hard for me to get used to. We're allowed to assume the Poincare conjecture nowadays. You see, it's been proved, so we can use it. And so, if we assume that, then again we get a nice characterization, if you like. I've talked about prime manifolds. Well, there's a purely algebraic characterization of such things, namely that again M is prime if and only if pi 1 of M is indecomposable with respect to free product. So let me in one direction, you see it's just the Knaser conjecture. If pi 1 splits non-trivially as a free product, then you get a corresponding connected sum where the factors have non-trivial fundamental group, and therefore they're certainly not the three-sphere. So this is just theorem 1.3. The other direction, of course, you need the Poincare conjecture. So that's just. Okay, so let me jump away from now until let's see, until corollary 1.10. So I'm not going to prove any of these things. I'm going to state them. Leave many of them as exercises for you. M will always be again a connected orientable manifold, but it not necessarily closed now until then. So there's another concept very closely related to primality called irreducibility. So you say M is irreducible if every 2 sphere in M bounds a 3 ball in M. And actually, this was the concept that Kneser used, actually. He didn't talk about primality. He actually talked about irreducibility, which is very interesting. And so here's an exercise for you. Again, M is not necessarily closed. Is that M is prime if and only if M is irreducible or there's exactly one manifold that's prime and not irreducible. S1 cross S2, right? So that's actually, for those of you who haven't seen this before, that's on the homework. You should be able to do that. Another well-known theorem in classical three-dimensional topology, so this is going to relate to irreducibility, is the sphere theorem. Let me mention that. So this is the sphere theorem. Sphere. Proved by Papakyriakopoulos. It says that, again, M not necessarily closed, but if you've got a 3-manifold M, if pi to M is non-zero, then in fact there's an embedded sphere. There's a 2-sphere S embedded in M, such that, which is not null homotopic, represents a non-zero element. So again, this was his famous theorem. He proved Dane's lemma. Dane's lemma was claimed by Dane in 1910. As I said, Kneser pointed out that Dane's proof was inadequate in 1929, and then it became a kind of famous problem. And it assumed a rather mythical kind of status, actually. People assumed that once you'd proved Dane's lemma, that would be the end of three-dimensional topology. Luckily for us, it wasn't true, right? But so, because Papakyriakopoulos did prove it in 1957, he also proved, well, he proved a version of the sphere theorem by a very similar argument, a famous tower construction. Beautiful, just absolutely beautiful, beautiful idea. Okay, and so so here's an exercise for you. You can now get a characterization of irreducibility now, again, purely homotopy theoretical, just like primality. You can express it in terms of the indecomposability of the fundamental group. M is irreducible if and only if pi 2 of M is 0. So that's another homework exercise. I warn you, this one's not so easy. One direction is easy. I won't tell you which direction it is. You've already probably figured it out. And as a consequence of this, because pi 2 behaves well with respect to covering spaces, you immediately get the statement that if you have a covering space, then then M is irreducible if and only if M tilde is irreducible. And again, actually, this was. Remember, we're allowed to assume the Poincare conjecture. I should mention that. This was known before the Poincare conjecture, but the proof was very hard. Let me just mention one more corollary here. again, this is an exercise for you. If m is irreducible and pi 1 of m is infinite, and m tilde the universal cover, then it follows that that m tilde is contractible. That's quite easy. I'll leave you to prove that as well. In fact, by Perlman, it's actually homeomorphic to R3. So that's not so easy, but so now we know that for irreducible manifolds, for closed, yeah, by the way, M is now closed, you see, right? It was only not necessarily closed up to cross rate 1.10. You've got to keep track of this. Okay, so there we are. In fact, like I said, M tilde is actually homeomorphic to R3, but that's much deeper. That's Perlman. And in fact, of course, as most of you know, much more can be said. I mean, usually, you can identify the action of pi 1 of m on R3 with the action with a discrete subgroup of disometry group of hyperbolic 3 space and so on and so on and so on and so on. But just a very basic statement. This is true. And a corollary of this, again, this is something you might think about. Exercise. It follows that if m is prime and pi 1 of m is infinite, then in fact pi 1 of m is torsion free. There are several different proofs of this, depending what you know, and you have to know something though. It's not immediately obvious, but there we are. Okay, so that's. Oh yes, let me just mention. Okay, good. Yes. If we go back to theorem 1.4, 3 manifold with finite fundamental group. Let me just remind you of a well-known example. These are the lens spaces. So let's take 2 integers, relatively prime integers. P is at least 2, and P and Q are relatively prime. Okay, then we can we can define an action of ZP. The cyclic group order P acts on, let's say, C2 by, well, you rotate the first copy of C2 through 2 pi over P. And the second copy through 2 pi Q over P. And of course, this is not a free action, but it fixes the origin. But its restriction to S3, the unit sphere, is free. In fact, obviously this is an action by SO4, and the quotient is the 3 manifold, and this is the so-called lens space LPQ. And so, of course, the fundamental group is just ZP. So these are a bunch of manifolds with finite fundamental group. So the fundamental group of the lens space depends only on P, and of course people naturally wondered, well, what about the homeomorphism type? Well, let me just state that in fact the homeomorphism classification is is more complicated, but let me just mention this, is that the two length spaces LPQ and LPQ prime are homeomorphic if and only if either Q is congruent to Q prime, plus or minus, I guess, plus or minus Q prime mod P, or QQ prime is congruent to plus or minus 1 mod P. Well, okay, I'm not going to go into this, obviously, but I mean, this is famously, well, in particular, L5-1 is not homeomorphic to L5-2. This was actually shown by Alexander much earlier. In fact, they are not even homotopy equivalent, you see, and so that was why that was done. However, and I often say that I think this was actually a very misleading fact. You know, one of the first things that people asked when they studied three-dimensional topology was to what extent the fundamental group determines the manifold. And well, they found that it's false. I mean, it doesn't, even for these length spaces. And so I think people then said, oh, well, in that case, it's probably going to be hopeless in general. You know, even for these really simple things, it fails to distinguish them. But of course, these are the only counterexamples, essentially. I always think an analogy that occurred to me a while ago is it's like it's like a very elementary number theorist testing the hypothesis. He's wondering whether all primes are odd. And he's, well, let's see. 2, it's false. Fails even for the first one. Hopeless. And so this is the, again, this follows from Perlman, that if M1 and M2 are three manifolds, and M1 is prime and not a lens space, and suppose that these guys have isomorphic fundamental groups, then in fact they're homeomorphic. So, I mean, I wanted to mention this because it's, I'm going to be talking here about the fundamental group of a manifold having a certain property. Well, the point is the fundamental group of a prime manifold determines the manifold, unless it's a lens space. So everything is somehow encoded in the fundamental group, if one could only unravel it. And by the way, let me not write this down, but in fact, there's another phenomenon. If you move away from prime manifolds, there is another phenomenon where you can have different manifolds with the same fundamental group. If you take a three manifold that's amphichiral, you know, it's not orientation preservingly homeomorphic to its mirror image. Call that M. If you take M connected sum M and M connected sum minus M, they have isomorphic fundamental groups, but they are not homeomorphic by the Knaser-Milner theorem, you see. But that's the point. The point is that modulo those sort of obvious counterexamples, namely lens spaces, and taking connected sums with non-amphichiral things, three manifolds are determined by the fundamental group. Okay, let's stop talking about three manifolds and move on to left orderability. So let me just, this is purely group theoretic now. We're going to switch gears and just talk about groups. So, yeah, so let me remind you that, okay, so I'm going to talk a little bit about left. So let me remind you that a strict total order, STO, on a set X So it's just a binary relation such that, well, it's transitive. You have transitivity x less than y, y less than z, implies x less than z. And then you have the, whatever it's called, trichotomy or whatever, that for all x and y in x, exactly one of the following. Well, either x is equal to y, or x is less than y, or y is less than x. Exactly one holds. So that's a purely set theoretic notion, strict order. And then if you have a group, so a left order on a group, so a left order on a group G, it's a strict total order on G, and the group structure just comes in and it's left invariant, so that G less than H implies FG less than FH. Okay, so that's a purely group theoretic notion, left order. And of course, if there is such a thing, you say G is left orderable, and so on and so on. And similarly, of course, you can define a right order. Similarly, you can define a bi-order, where the order is invariant under right and left multiplication. So similarly, of course, an obvious usually let me just, it's hard to give, at this point, sort of non-trivial examples, but let me just give a very obvious example, is that, obviously the additive group of the reals is bi-orderable, right, with respect to the usual it's abelian. Most of the groups we're going to be dealing with, of course, are non-abelian. One of the homework questions is that G is left orderable if and only if G is right orderable. So, of course, a left order won't usually be a right order, but nevertheless, left orderability is equivalent to right orderability. And I guess I can't resist saying that in Texas, we prefer to talk about right orderability. But I'm from Austin, and so I'm going to talk about left orderability. Because we need it. Okay, anyway, okay. Enough of this. This is on tape. Oh, ridiculous. All right, okay. They'll take away my NSF grant. All right. So here's a very elementary lemma that not all groups are left orderable. So G left orderable implies G torsion free. So remember, I actually took the. I made a point of mentioning that if you have an irreducible, if you have a prime three manifold with infinite fundamental group, then in fact its fundamental group is torsion free. But this is of course elementary. I mean, suppose you've got some element. So suppose you've got G in G that's not the identity. Well, let's suppose it's greater than the identity. Well, you see, you can multiply this on both sides by G, right? So G squared is greater than G, right? But G is greater than 1, you see. And because of transitivity, G squared is greater than 1. And so therefore all the positive powers of and so you're never going to be the identity. And similarly if G is less than 1, of course. So very elementary there. Now, of course, the converse, as we'll see much later, is far from true. I mean, there are many fundamental groups of three manifolds, rational homology spheres. So they're going to be prime, and they're going to have infinite fundamental group. And so in particular, it'll be torsion free, but they won't be left orderable. So Let me. Okay. Yes. So let me. Okay. One aspect of left orderability. There's actually a topological aspect to it. You can put a topology, and it's very useful. I'll say a little bit about this. You can put a topology on the set of left orders on a group. And if one way to, the way to do this is to say that if you have a left order on a group G, then you can talk about the positive cone. It's just a set of elements that are greater than the identity. This is called the positive cone. Of the left order. And the point is that you can identify left orders with positive cones. So left orders are just particular subsets of the group, and so therefore you can topologize the set of left orders. I'll say in a minute. So here's an elementary thing that the positive elements are closed under multiplication, and also the group G is partitioned into the positive elements, disjoint union the negative elements, which is these are the set of things G inverse. By the way, G is greater than 1 if and only if G inverse is less than 1. But you can prove that. Be careful. It's not true that G is less than H if and only if H inverse is less than G inverse. Think about it. That's true for biorders, but it's not true. That's sort of canonical mistake 1. You can prove all kinds of things about left orders if you assume that. And so you get this. So again, this is an exercise, an elementary exercise for you that I've put on the thing. And so you can now talk about, well, conversely, if you have a subset P with those properties, that actually induces a left order. So let me again mention that. So let's just call a subset P of the group G, let's say is a positive cone if it satisfies those two properties. And then the exercise is that elementary exercise for leaf to you is that so P in G a positive cone, then you can define a left order by saying G is less than H if and only if G inverse H belongs to P. This defines a left order whose positive cone defines a left order on G whose positive cone is just P. So again, that's a elementary exercise for you. There's a nice dynamical interpretation of left orderability, and it's very, very general. But it's important, actually, when we come to talk about fundamental groups of 3 manifolds. But here's the following. So let's just take an arbitrary set X and with a strict total order. Then we can look at the group of order-preserving bijections of the set X, right? So this is the group under composition, right? This is the group of preserving bijections of X. Well, such a group is always left orderable. So again, the details of this are going to be left to you, but let me tell you what you do, and then you have to check that it works. Okay, well, what you use Zorn's lemma. You use, if you don't mind using Zorn's lemma. Anybody object to using it? Oh, it's too bad. Anyway, so you choose a well order. So let's call it this. Be a well order on X. And now suppose you've got two bijections that are not equal. Two order preserving bijections that are not equal. Well, that means they disagree on some set. So if you look at the set A, the set of X, such that they disagree, this is non-empty. A non-empty subset of X. So it has a least element. So with respect to this well order, so let X0 be the least element of A with respect to. And then you then declare that F is less than G if and only if, so you're defining this, but if and only if F of X0 is less than G of X0. This is the order on, the strict total order on X. And then your exercise is to prove that this is a left order on okay, this is all a bit general, but a nice example of a set with a strict total order on it is the reals with the usual order. And so we can apply that theorem there. And let's just notice, so again, here's an exercise for you. Well, anyway, so let this be the standard STO on R. And I call this a... Well then, in fact, the order preserving bijections they just have to be homeomorphisms. And so this is actually just the orientation preserving homeomorphisms of R. That's another exercise. And so you get that the group of orientation preserving homeomorphisms of the real line is left orderable. Now I should have mentioned, but it's completely obvious that left orderability is inherited by subgroups. Okay, I mean a left order on a group will induce a left order on the subgroup and any subgroup. And so any subgroup of homeo plus R is left orderable. And in fact, there's actually, it turns out that this is rather interesting. There's actually, there's a sort of converse to this. Well, so let me just say that, so any G that's a subgroup of homeo plus R is left orderable. And in fact, a theorem which I won't attempt to prove, or I won't even give it as an exercise, but I'll just state it. For countable groups, oh, by the way, I should have said perhaps, yeah, I mean, this is, well, it doesn't matter. Okay, let's leave it right now. Okay, fine. Yeah. For countable groups, there's actually a complete sort of characterization of left orderability in terms of this. So G countable, then G is LO if and only if G embeds in homeo plus R. So G is isomorphic to a subgroup of homeo plus. These are the orientation preserving homeomorphisms. Like I said, one direction follows immediately from this. The other direction is perhaps a little bit more impressive, but the proof isn't that difficult, actually. I mean, when you see it, you take a countable left orbital group, you can actually embed it in homeo plus R. You have to be a little bit careful, but it works. Okay, so so this is going to be nice. You see, well, let me say somehow. I mean, okay, this is just the easy direction is going to be very useful, because if we've got a 3-manifold and we suspect or we'd like to prove that its fundamental group is left orderable, if we can get that fundamental group to act on the real line, by orientation preserving homeo. Well, if we can get it to act faithfully, then that means it is isomorphic to a subgroup of that, and therefore it's left orderable. Now it turns out, and again, this is something I'll discuss in the next lecture, a special fact about prime 3-manifolds is that you don't have to have a faithful action as long as the action of pi 1 on the real line, as long as it's non-trivial. So in other words, the fundamental group will have some non-trivial quotient that is a subgroup of homeo plus. That turns out that's enough. And so the fundamental group will be left orderable. So that's going to be a key fact that we will use to prove that certain fundamental groups of 3-manifolds are left orderable. We'll get them to act on the real line. Okay, let's move on. Okay, so let me continue. This is good talking about left orderability. Let me come back to what I alluded to a little earlier, that you can actually topologize the set of left orders on a group. Let's let me mention this. Now again, I'm not going to give any details of the proofs really, but so let's define L for a group G. Let's define LO of G just to be the set of left orders, but we'll think of this as the set of positive cones, right? In G, and of course, so that's a subset of the power set. The power set of G. This is the set of all subsets of G, right? And of course, you can topologize this. This is 2 to the G, right? Well, now this is very famously, this space is compact. You see, this is compact by the Tikhonov theorem. Now, you can also yes, you take the product topology on this, right? You just make sure that all the smallest topology so that all the projections are continuous. Well, you can prove, in fact, this is one of your exercises, although it may not be that obvious. You can prove that the set of positive cones is actually a closed subset. And so therefore it's compact. So this is a kind of key, rather a key point. Again, I'm not giving any details, but using this compactness, and I think maybe at least it might make sense that compactness might be used to prove something like this. So this can be used to show. So here's how am I doing? 1.21. Okay. Right. There's a that you can characterize left orderability of a group just in terms of its finite subsets. I mean, so if and only if for all finite subsets F in G, you can sort of. Well, sorry, let me, okay, yeah, sorry, I should have given a little definition before that. Sorry. Well, just a little definition. If I've got a subset X of group G. So let S of X, this is the semigroup, you know, generated by X. So it's just a set of non-empty products, right? Products of non-empty, you know, of elements of X. Okay. Okay, and so like I said, this theorem then is that left orderability, G is left orderable if and only if, for all finite subsets, I can sort of left order them. In other words, I can say which of them are positive and which. So there exists a function epsilon from f to plus or minus 1 such that if I look at the semigroup generated by the set of elements, I take all the elements of f and I raise them to this either plus or minus 1. See? This does not contain the identity. I never get the identity. So clearly this is true if you are left orderable. Obviously, you just define epsilon. Sorry, f is a it doesn't contain the identity. Sorry, f is a finite subgroup. You just define epsilon according as x is positive or negative, right? But the converse is true. So in other words, this is very useful actually. I mean, as I say, you could perhaps imagine that the compactness of this is going to be used, could be used to prove something like this, that you can detect left orderability just on finite subsets. And this is the basis of, so what it means is that if you have a group that's not left orderable, you will be able to detect that on some finite subset. And so this is the basis of a program, Nathan Dunfield has a computer program that you give it a finitely presented group and it will just start looking at larger and larger finite subsets and check this. And if the group is not left orderable, it'll usually quit in a fraction of a second and say no. And if it keeps running, well, you suspect that the group might be left orderable, but of course that's no proof. But, so that's sort of interesting. And let me just finish by saying that in turn, this theorem in turn, can be used to prove, and again, this is, remember, ultimately, next time I'm going to talk about fundamental groups of free manifolds, and I'm going to prove this theorem that if you have a prime 3 manifold, then the fundamental group is left orderable if and only if it has some non-trivial action on the reals, you know. And so one of the algebra, there's going to be some three-dimensional topology involved in that, but there's also going to be some algebra, and the algebraic fact is going to be the Burns-Hale theorem, which you can prove using, again, it's not a long proof, but it would take too long to give it here, using this characterization, theorem 1.21. So again, using this, in turn, one can show, and so this is going to be the last theorem I'll mention today. This is the Burns-Hale. Is that G is left orderable if and only if for all finitely generated H not equal to the identity. For all finitely generated subgroups, H has a non-trivial left orderable quotient. So in particular, this says that, this says that left orderability is a local property. If every finitely generated subgroup is left orderable, then the group is left orderable. But in fact, it's more than that. It's enough for every finitely generated subgroup to have a left orderable quotient. And so this is, as I say, you can actually prove this fairly easily from this statement. And that might be a convenient place to stop. go again. Okay, so earlier today I talked a little bit about the decomposition of three manifolds into prime subbands and so on. I talked a little bit about left orderability, stated this Burns-Hale theorem. Let me at this point make the convention, it's sort of a convenient for this conjecture to make the convention that the trivial group is not left orderable. Okay, so this is just the trivial group in which case we can now erase this. Right. Okay, so let me just make draw a couple of corollaries of this Burns-Hale theorem, and then I'll start talking about three manifolds and how we can perhaps try to prove that they have or have not left orderable fundamental groups. So, right. So okay. Let me put this up here, maybe. So there's another group theoretic definition is indicability. A group G is indicable if and only if, well, either G is trivial or there exists an epimorphism from G to Z, and we'll use this concept in a minute when we talk about three manifold groups. But let's just notice a corollary to the Burns-Hale thing here is that if a group is locally indicable, so G locally indicable implies G left order. Let me remind you that, I mean, locally, G as a product locally if every finitely generated subgroup has the property. And, well, that's immediate, right? Because if G is locally indicable, then every finitely generated subgroup, if it's non-trivial, it maps onto Z, and Z is left orderable. So that's an immediate consequence of the Burns-Hale theorem. And yeah, let me just mention that because it's used in one of the homework problems. A corollary of this is that free groups are left orderable. Every subgroup of a free group is free, so if you have a non-trivial free group, obviously it maps to non-trivial finally generated free group. It maps to Z. So free groups are left orderable. In fact, they're bi-orderable, but that's a bit harder to prove anyway. So, but at least it follows from this. Okay, so let me sort of start again now. Well, and start talking about. Don't know why am I doing this? Okay, so let's just start talking about left orderability and three manifold groups. Okay, so left. So we're going to be so this is a new chapter or whatever. Okay, so yeah, so let me just consider the following property. So let's just, yeah, okay, so consider the following property for group G let me call this property star, whatever. Every finitely generated subgroup it's almost like locally indicable, but not quite. Every finitely generated subgroup of G of infinite index is indicable. So that's a property that may or may not hold for a given group. But let me just prove a couple of things about this property. Well, first of all, let me prove that so let me call this maybe I'll call this proposition 2.1. Suppose you have a group G that satisfies this property. Then I claim that G is left orderable if and only if G has a left orderable quotient. So then G is LO if and only if G has an LO quotient. And remember, we're now making the convention that the trivial group is not left orderable, so that's okay. So this is very easy. Well, I mean, we're going to use the Burns-Hale theorem. We're going to take a finitely generated. Well, okay. Let me. Obviously, one direction is trivial, right? So. But for the converse, we'll use Burns-Hale. So we want to take a finitely generated non-trivial subgroup and prove that it has a left orderable quotient, right? So let H finitely generated non-trivial subgroup of G. Okay, well, there are two cases. H may have infinite index, in which case the hypothesis gives us what we want. So if G, H is infinite, well, every subgroup of is indicable. So G and H is non-trivial, so there exists an epimorphism from H to Z, and Z is left orderable, and so H has a left orderable quotient. If the index is finite, well, we want to use the Burns-Hale theorem. So we want to show that right. Sorry, we're sorry. We're right. We're assuming that G has a we're assuming that G has a left orderable quotient, right? And so right. So by hypothesis, there exists an epimorphism phi from G to Q left orderable, right? That's our hypothesis. We're trying to prove that G is left orderable. So there's an epimorphism from G to now. Q is left orderable, so it's non-trivial. So well, it's infinite. So Q is infinite. But H has finite index in G, and so therefore phi of H is non-trivial subgroup of Q. Well, so there you are. That is your left orderable quotient, right? therefore phi. Okay, so we've shown that the hypothesis of the Born-Sale theorem is satisfied. Every finitely generated non-trivial subgroup has a left orderable quotient, and so therefore G is left orderable. Okay. So that's that property star is all we need. And so now the important thing for three-dimensional topology is that if you have a prime three-manifold, closed three-manifold, then in fact the fundamental group satisfies that condition. So remember our convention that if all three manifolds are closed unless I say otherwise, so let M be a prime three-manifold. Then whatever satisfies every subgroup of infinite index is indicable. So immediately then, I'll come back and prove this in a minute. Well, a few minutes. But let us just note then that, well, I'll leave this here. Let's go to so these two propositions imply that so this is the what are we doing here? 2.3 is it? So this is a theorem of Boyer, Rolfson, and Riest. Just an immediate consequence. Then pi 1 of m is left orderable if and only if pi 1 of m has a left orderable quotient. Okay, so this is obviously something very special about, well, not obviously, but it is very special for prime three-manifold groups. This is not something you'd expect to be true for arbitrary groups, but it is under this hypothesis that every finally generated subgroup of infinite index is indicable. So let's just draw, before we get to prove, all we need to do is prove this proposition, right? But before we get to that, let's just draw a couple of corollaries of this theorem. So the first is that if the first homology of M is infinite, then pi 1 of M is left orderable. Well, because H1 of M infinite implies that H1 of M maps onto Z. It's just a finitely generated it's a finitely generated abelian group. It's infinite, so it maps onto Z, so pi 1. Which is left orderable. So it has a left orderable quotient, and so it's left orderable. So that's already this question about left orderability, assuming that it's interesting at all for three-manifold groups. If the first homology is infinite, then the game's over. So the only interesting case will be when the first homology is finite. In other words, if you're a rational homology sphere, as Adam was talking about this morning. So that's one corollary. The other corollary, which is which we'll also use.
Is there an easy example of an non-free manifold group that, just to have in mind, for which this hard direction of Boyer-Wilson-Weiss doesn't?
Yeah, well, I mean,
It has a left orderable quotient, but it's
Z plus Z mod 2.
yeah. Wait.
okay. But then you can refine the question. Yeah. Yeah. By the way, I mean, again, that shows, well, that doesn't, but I mean, even for three manifold groups, you have to say prime, right? I mean, if you take, you take a connected sum of something with a length space, the something might be left orderable, but because you've got torsion in that other sum, and this will have a left orderable quotient, namely the guy that the other guy, but it won't be left orderable. So of course you need prime. Yeah, that's right. Mm-hmm. So the other corollary is that, again, we're going to use this, is that so again, M is a prime 3 manifold. Close. And pi 1 of M is left orderable if and only if there exists a non-trivial orientation preserving action of pi 1 of M on the real line, right? So this is really, of course, it's the right to left implication that we're going to use, but the left to right happens to be true as well by a theorem that I mentioned but didn't really prove. But I mean, pi 1 of M is countable, so pi 1 of M is it's a countable left orderable group, and so therefore it actually embeds in homeo plus R. That was a theorem which I mean this is not so important. I mean, but just to be logically complete, that was theorem 1.20. I just mentioned that, but it's the converse direction which I did prove, which is going to be useful, of course. But let's just spell it out. It's pretty obvious, right? If you've got a non-trivial orientation preserving action, well, that means that we have a non-trivial homomorphism from pi 1 of M to homeo plus R. That's exactly what it means, so it's be non-trivial. So I pointed out in the lecture this morning that, the the group of bijections of a sort of totally ordered set that preserve the total order is always left orderable. So in particular, this guy is left orderable. And so this is a non-trivial, and so any subgroup will be left orderable, right? So then phi of pi of M, the subgroup, it's not trivial, subgroup of homeo plus R, and so it's left orderable. So this is an LO quotient of pi 1 of M, so therefore pi 1 of M is left orderable. So that's something we'll see is very useful. By the way, just a sort of remark. I mean, remember the proof that homeo plus R is left orderable just involves, like, well, the way I said it, you can do it a little differently, but the way you just choose some well order on the reals, and you get, and so I mean, clearly there are uncountably many ways of doing that, and so you get uncountably many left orders on this. Actually, I mean, it's a very kind of soft property. In fact, that's an interesting fact about left orderability, that a group the number of left orders on a group is either uncountable or 2 to the n, which is a nice fact. So for n finite. Right? Okay, so let us now prove. So the main work now is to prove proposition 2.2 that a prime 3 manifold satisfies that every finite general sum with infinite index is indicable. So now we have to do a bit of topology. So let's prove. Okay, so let's prove proposition 2.2. Well, the first thing is, okay, I've said prime. I mean, remember, prime and irreducible are pretty much the same. The only difference is S1 cross S2. Well, the fundamental group of S1 cross S2 is Z, so that's left order. So we're okay. So, so M not prime. Sorry, M not irreducible, right? Implies M. S1 cross S2, Y1. So we're happy. So let's assume that M is irreducible. Okay, we've got this finitely generated subgroup, H. So H of pi 1 of M. And we want to prove that it's indicable. Indicable means it's either trivial or there's a epimorphism Z. So let's assume it's non-trivial. We've got to prove that it maps onto Z. Okay? The finally generated subgroup of infinite index. Okay, well, it's a subgroup, so it corresponds. There's a corresponding covering space. So let M tilde M be the okay. So let's notice infinite index. We need to use that. Infinite index means that M tilde is non-compact, right? Okay, that's the first thing to notice. Now the second thing is that there's a theorem, because pi 1 of M tilde is finitely generated. There's a classical theorem in three-dimensional topology, the Scott-Core theorem, that says that if you have a 3 manifold whose fundamental group is finitely generated, then there's a compact submanifold whose inclusion induces an isomorphism of fundamental groups. That's a classical theorem. Classical. So H, so pi 1 of M tilde finitely generated. Therefore, that's the Scott-Core theorem. So I won't say any more about this. That, by the way, it's an interesting exercise. You might prove the two-dimensional version of that. I mean, if you've got a surface whose fundamental group is finitely generated, prove that it has a compact core, has a compact subsurface, and that will be a warm-up problem for the Scott-Core theorem. Anyway, by the Scott-Core theorem, that there exists a compact 3-manifold N in M tilde, such that the inclusion map of this into pi 1 of M tilde is an isomorphism. Okay, that's the Scott-Core theorem. So I won't say any more about that. Okay, so now let's look at this. We'd better use the irreducibility of M. So now we're going to use it. So how are we going to use it? Well, let's look at this compact submanifold. Let me draw a picture, maybe. So This is just some compact submanifold. So there's bits, there's bits of the manifold. It's M tilde is non-compact. So N's a compact manifold. It definitely has boundary, but right. So, well, let's put it this way. So first, suppose S has a two-sphere boundary component. So suppose N has a two-sphere boundary component. S. Well, our assumption is that M is irreducible, and so if you remember, one of your homework problems was to prove that a covering of an irreducible manifold, because irreducibility is equivalent to the vanishing of pi 2. M irreducible implies M tilde irreducible. So that means that this two-sphere bounds a three-ball in M tilde, right? So therefore S, the boundary is B, now, if you think about it, this B could not contain N, because in that case, pi 1 of N would factor through pi 1 of B, which is trivial, but pi 1 of N is H, and H is non-trivial. So pi 1 of N, H equals pi 1 of N not trivial, implies B doesn't contain N. So that means that B is on the other side of N. So B is over here. And so we could just cap off N, that boundary component, with B. So you can replace, and of course this doesn't affect the fundamental group, so we can replace N by N union B, and we still have the same properties. And so that means we can assume that N has no two-sphere boundary components. So therefore, may assume boundary N has no S2 components. But the boundary of N can't be empty, because if the boundary of N were empty, then N would be the whole of M tilde, right? But M tilde is non-compact, right? Right? Since N compact and M tilde non-compact. Okay. So there must be some boundary components. And now it's a familiar exercise that if you have, let's say, a compact 3 manifold and it has a boundary component of genus greater than 0, the first homology must be infinite, right? So using Poincare duality or Lefschetz duality or something. So let me just write down the answer and then say something about this. So therefore boundary N has a component of genus greater than 0, and therefore the first homology of N is infinite, and therefore the usual argument maps onto Z, and so therefore H, which is pi 1 of N, has quotient Z. But that means it's indicable, right? So therefore. So we started with a non-trivial, finitely generated subgroup of infinite index of pi 1, and we've shown that it maps onto Z. So that was enough to, that's property star, which is enough to get us the, the theorem which I guess I've erased. Yeah, so by the way, I mean, I'm sure most of you have seen this property that if you have a three-manifold with a boundary component of positive genus, the first homology must be infinite. I mean, it's essentially duality. I mean, if you take, I suppose you got a torus, just for simplicity. So you look at a basis for the first homology, alpha and beta, and see, they can't both die. In fact, they can't. I mean, you know, I mean, they have. If you take any multiple of alpha and any multiple of beta, they have non-zero intersection number, and so none of them can be zero homologically in the three manifold. I mean, sorry, they can't both be. They can't both be. It's this business of, you know, if you have, let's say, take the simple case, just look at alpha and beta. Could alpha and beta both be null homologous? Well, there would be a surface whose boundary is alpha. There'd be another surface whose boundary is beta. What does the intersection of those two surfaces look like? Well, it's a bunch of simple closed curves and arcs, but there's only one intersection point, so you'd have an arc with only one endpoint, and that's impossible. So, of course, a fancy way to say all that is Poincare duality. Okay, but that's the Boyer-Rolson-Weiss theorem, and so this is going to be very useful. That if we can prove that, if we ever prove that our three-manifold group, you know, has a non-trivial, has a left-orbital quotient, then in fact it's left-orbital. In particular, if it acts on the real line. So this is okay. At this point, let me. Okay. Sorry. Yeah, okay. Let me do something else. All right. Now I know Rachel's going to be talking about foliations, but I guess let me just give us some sort of very brief definition and say something about this. I know she's going to be saying much more. So this is going to be very, very informal, but let me just say something about that. So let's just say the following. So we're going to well, it's always going to be codimension one foliation F on a three-manifold M. So that means a closed three-manifold. Well, again, without going into too many technicalities, it's just a, you know, it's a, I mean, it comes from a covering of M by compatible charts of the form. I mean, the charts, of course, are R3, but then you have these So you know, you just have this foliation of the charts by horizontal planes. And these have to be, that sort of product structure has to be compatible. I won't say any more about this. Rachel's going to say much more about this, but I hope you sort of get the idea. And of course, these glue together. These T cross R2s glue together to form the leaves. You get these two-dimensional leaves. So of course a very simple case of such a foliation would just be take a surface cross S1. Okay, but that's not interesting, it turns out. I mean, that's not interesting. For us, it's not interesting. In our case, the leaves will all be sort of non-compact and so on. But that's the. Now again, even this definition is not particularly interesting because it turns out that every three manifold has such a thing. So every three manifold. He's not here. He was here. So this is Licorice, I think, and Novikov maybe. Well, the thing is that there's a thing called the Rabe foliation, which is a slightly bizarre foliation of a solid torus that you can use to prove that every three manifold has a foliation. So in some sense, this is not a pretty interesting concept. However, if you if you impose an extra condition, then it turns out to be interesting. You say that f is taut. I know Rachel's going to say much more about this and say it all much more precisely, but I just wanted to get the general flavor here because I wanted to say something. Okay, f is taut if there exists a simple closed, well, there's a loop, let's say gamma in M, which meets each leaf of f, and it meets each leaf transversely. That's kind of the key point. So that's turns out that's really a non-trivial condition. Not every three manifold has a taut foliation. And by the way, there's one other a sort of fairly minor thing, but that sort of orientability condition. So you say that the foliation is co-orientable. So I mean, or orientable, whatever. I don't know. F is co-orientable. You know, there exists a consistent, transverse orientation. So in other words, everything, all these charts are oriented in the obvious way, and everything's kind of orientable. So there should be a consistent sort of normal. Okay, and so now I think we've got all the words in place, and we say that. So M is CTF, co-orientable taut foliation, if M has a co-orientable taut foliation. Okay, so right, so let me come to this here. So this, I just mean pi 1 M is left orderable, and I've just said what this means, and this means that E is not an L space. Adam defined L space this morning, and he may say more about it. Okay, so we'll say more about this a bit later, but let me at this point just say that if the first homology of M is infinite, so again this is just so this conjecture is true if the first homology of M is infinite. Now why is that? Well, you see it's left orderable, right? Pi 1 of M is left orderable because that was, if H1 of M is infinite, that was a corollary, actually said that maps onto Z, pi 1 maps onto Z, which is left orderable. So that was actually corollary 2.4, right? The consequence of the Boyer-Rolson-Weiss theorem. It turns out that M always has a co-orientable taut foliation, and this was sort of famous work of Gabay back in the 80s. I don't know, 90s or so, I'm not sure when. And finally, well, M is not an L space. I mean, that's just by definition, I guess. I mean, an L space, by definition, is a rational homology. So again, for these properties, the case where the first homology of M is infinite is sort of uninteresting for one reason or another, and so we just focus on the case where the first homology is finite. In other words, M is a rational homology sphere. So,
is there a good counterexample when M supports a non-co-orientable taut foliation? Good meaning easy to say in the next 20 seconds.
Where's Rachel?
So what was the question?
All manifold, right? Is there a good example of an M with non-co-orientable taut foliation that breaks the conjecture?
It's a taut foliation, but it's not Coordinable.
Yes, because if you take a surgery on minus 237, belief suspension you can get, arbitrarily high acute which is
Thank you.
Okay, so like I said, so the interesting case, so assume h one of m is finite, i.e. m is a rational homology sphere. And again, let's look at the case. Remember, m is a prime manifold. There are two basic cases, pi1 of m finite and pi1 of m infinite. So let's just look at the case when pi1 of m is finite. Well, remember, if you're left orderable, a left orderable group is torsion free. So, and remember, the trivial group is not left orderable. So, pi1 of m finite, then m is not left orderable. That's just because that torsion free, that was lemma 1.15, I think, way back. So that's obvious. And it turns out that also m does not have a coordinable torque foliation. This is a theorem of Novikov, I think, right? That this transverse loop in the definition of tautness actually has infinite order in pi1. So, and again, what about L space? Well, it turns out that all these guys with they're all L spaces. And of course, this depends on, this was proved by Oswath and Szabo, using Perelman's theorem, and using the fact that the manifolds with finite fundamental group are precisely the ones that we know and love, the ones that come from the three-sphere by, action by a finite subgroup of SO4. So again, this case is not interesting. Well, in the sense that it's these things are all equivalent there. So again, the interesting case is that you're a prime rational homology sphere, and pi1 of m is infinite. And so this is the interesting case. As I said, m is a rational homology sphere, prime, and pi1 of m is infinite. And now things do get interesting. I mean, first of all, very little is known about this. I mean, having got rid of the sort of trivial cases, we're left with this kind of thing. Let me just say that, you see, we saw that if the first homology is infinite, then, they're always left orderable, they're always blah, blah, blah. And if pi1 is finite, then they are never, whatever. But here, there are examples where everything, where these properties do hold, and there are examples where they don't hold. So it is interesting. And so, for example, let me just give there exist such manifolds M1, M2 with, just as an example of, I mean, maybe if you haven't seen these things before, it just shows it's a little bit hard to tell just by looking at the group. So here's a nice finitely presented group. In fact, here's another one. There are actually three manifolds with these fundamental groups. So here's a very similar presentation. Let me just change that 4 to a 6. Well, it turns out that the first manifold, that group is left orderable. The manifold has a coordinable torque foliation, and it's not an L space. On the other hand, the second guy is not, the group is not left orderable, and it doesn't have a coordinable torque foliation. and it is an L space. So, but I just think that, you know, group theoretically, if you thought you could understand whether or not a group is left ordered just by looking at it, I think you'll agree it might be kind of hard. I mean, these look awfully similar, but it is different. By the way, I should perhaps say, and I know the other lecturers are going to say much more about this, but right. The one sort of implication among these conditions that is known sort of unconditionally is, so it's a fact that, well, it's a fact that if M has a coordinable taut foliation, then it's not an L space. And so this was, is it? Oh, it's OZ, right? Yeah. Oh, sorry. Sorry. Basically, it was Masabo using a result, and I know Rachel's going to talk more, but I think Andy might be talking about this too. It's a long story, and they'll say much more about this, but I'll just mention this here, that using a theorem of Eli Ashberg and Thurston, showing that coordinable taut foliations give rise to certain contact structures, they proved that if you had a coordinable taut foliation, then you couldn't be an L space. Unfortunately, there was a certain kind of smoothness conditions in that the foliations had to satisfy that wasn't necessarily true for the foliations that people were producing. And again, Rachel's going to say more about this. And so, strictly speaking, this needed more recent work of Cazes and Roberts and Bowden to remove those smoothness conditions from the foliation. So now we can say, without any qualification, that this is true. But that's the only implication that's sort of known in general. And then, the situation is that for certain classes of manifolds like this, I mean, we know perhaps one of these properties, perhaps two, but we don't know the third, or and so it's a nice challenge that yeah, sorry.
Do we know if some of those properties are generic in some sense in this family?
Well, I mean, that's yes. I mean, I think it's kind of weird, right? I mean, L spaces are very special, right? So you'd think not being an L space would be generic. Well, that means that having a left orderable fundamental group is generic, but I mean, it sounds like it shouldn't be, but I guess for three manifolds, maybe it is. I mean, yeah. So I think, yeah. I mean, I think all these properties should be generic. Yeah. Because L spaces, yeah, they're very, very special. I mean, the Hagar-4 homology is really minimal, But it's somewhat surprising. Because, like I said, if you didn't know anything about this, asked about left orderability, you would say, well, that's non-generic. But for three manifolds, it seems to be generic, at least conjecturally. Let me just mention one. Okay, let me just do one more thing before I quit here. And again, I know Rachel's going to be saying much more accurately things about this. But let me just mention one more fact about foliations that's relevant here. So suppose we have a coordinable taut foliation F on our manifold M, and again, well, okay. I mean, I know we're in some prime manifolds, but there's a general sort of fact that if you stay away from these two guys, there's a theorem. Oh, well, yeah. Maybe I should. Yeah, let me first say that if you have a foliation, then you can form what's called the leaf space. So if F is a foliation on M, you can get a quotient map. You get a quotient map from F to let's call it lambda F, the leaf space of F. Just by identifying each leaf to a point. and take the quotient topology. This is usually a horribly, well, this is usually an uninteresting space topologically, but you could at least do that. And so here's a theorem that under the circumstances, this is due to Novikov, I believe, Rachel will, I think it's due to Novikov and Palmera, that the universal covering, if you take a coordinate foliation on any three manifold, it's not these guys, then the universal covering and the lifted foliation on the universal covering, well, the universal covering is just R3. Actually, more than that. Sorry, this is actually a foliation on R2 by lines across R. So this is a foliation on R2 by copies of R, and you can see then that, well, the leaf space, the leaf space is just going to be the leaf space of this guy. So the leaf space of F tilde is the leaf space of L, and it's pretty easy to see that this is a one-dimensional. This is a simply connected. It's a simply connected one-dimensional manifold. Unfortunately, it's not necessarily Hausdorff. Easy examples to see. So you would like this simply connected one manifold to be the real line. I mean, that's what you imagine it should be, but it isn't necessarily. But if it is, then you give that foliation a name. So if the leaf space, if this is homomorph to R, then you say that F foliation is R covered. And let me just finish then with the statement. This brings it all together a little bit. That if you do have a foliation, if our prime three manifold, whatever, if our three manifold M has an R covered foliation, so this provides some connection between the two properties that were there on the left. So the theorem that if M has an R covered foliation, then pi 1 of M is left orderable. And if the proof is this is nice way to finish, because it brings together what we said. Well, if you have an R covered foliation, I mean, the fundamental group acts on the universal covering, which of course is R3. I mean, but okay, but it doesn't really matter so much. But it acts on the leaf space. Therefore, the leaf space of this lifted foliation, which we're assuming is R. So you get this action of the fundamental group on the leaf space. Now, it's clearly a non-trivial action because the quotient is compact, and it's orientation preserving because of this co-orientability condition. So co-orientable implies orientation preserving, and of course it acts non-trivially. And so there we are. And so we have so therefore, I mean, that's what I just said. So yeah, there exists a non-trivial homomorphism from pi 1 of M to homeo plus R. And so therefore, by the Boyer-Rolson-Weiss theorem, we have this non-trivial. Well, I mean, I guess I gave a corollary that has to. Okay, so that's a good place to quit. But so, like I said, that shows that at least, maybe there is something in this conjecture. At least if the foliation you're looking at is nice, in this sense that the leaf space and the uniform covering is just R, then in fact that does imply left orderability. And next time I'll talk a little bit more about these things in the context of Seifert-Fibert spaces, where everything is known there. It's known that this conjecture is true. All these three things are equivalent, and I'll say something about that.
Maybe we have another coffee break. Then we'll convene in half an hour.